Classical physics, which had dominated scientific thought for centuries, was based on the belief that the universe operated in a deterministic and predictable manner. This approach was rooted in the laws of motion formulated by Isaac Newton, who suggested that if the position and velocity of an object were known precisely, then its future behavior could be determined with absolute certainty. The idea of a predictable universe where everything operated according to fixed laws gave rise to a sense of control and order. The precision and certainty that classical physics promised were foundational not only to the development of science, but also to the human understanding of nature. Under classical physics, scientists believed that the world was like a giant machine functioning in a predictable and ordered way. Every object, whether it was a planet moving through the cosmos or a rock falling to the ground, was thought to follow a specific set of rules that could be mathematically modeled. For centuries, this view of the universe shaped scientific inquiry, from the formulation of Newton's laws of motion to the understanding of planetary orbits and the very nature of matter. In this view, as long as scientists had enough data about an object's position, velocity, and forces acting upon it, they could, with sufficient calculation, predict its future. The equation for this type of certainty seemed complete. Yet, as the 19th century turned into the 20th, advances in scientific thinking began to challenge this long-held view of certainty. The development of electromagnetism, the discovery of the electron, and the advent of new mathematical tools led scientists to delve deeper into the microscopic world, the world of atoms and subatomic particles. This was the birth of what would become known as quantum mechanics, a field that defied the classical assumptions of predictability and certainty. The behavior of tiny particles, such as electrons and photons, seemed to defy the rules established by Newtonian physics. The first hints that the classical view of a deterministic universe might be incomplete came from the study of blackbody radiation. In the late 19th century, scientists observed that the radiation emitted by heated objects did not match predictions based on classical physics. The existing theory, based on classical electromagnetic laws, predicted that objects should emit an infinite amount of energy at shorter wavelengths, a problem known as the ultraviolet catastrophe. This paradox led to the realization that classical physics was unable to fully explain the behavior of energy at the atomic and molecular level. The German physicist Max Planck, in an attempt to resolve this issue, proposed a radical idea. Energy was not emitted continuously, but rather in discrete units called quanta. This concept, which laid the foundation for quantum mechanics, introduced the notion that the universe at a fundamental level might not follow the smooth, continuous laws of classical physics, but instead operates on a probabilistic and discrete scale. At the same time, Albert Einstein's work on the photoelectric effect further challenged classical physics. Einstein demonstrated that light, which was traditionally thought of as a continuous wave, could also be thought of as a stream of particles, or photons. This dual nature of light, as both a wave and a particle, suggested that classical concept of determinism might not be enough to explain the complexities of the atomic world. The shift from a deterministic to a probabilistic view of the universe was becoming clearer, but it still wasn't enough to fully overthrow the classical paradigm. The breakthrough that would fully upend the certainty of classical physics came in 1927 when Werner Heisenberg, working in the framework of quantum mechanics, developed what would become known as the Heisenberg uncertainty principle. Heisenberg's insight was simple yet profound. In the world of quantum particles, there are limits to how precisely we can measure certain pairs of physical properties, such as position and momentum. Heisenberg's work built upon the earlier work of scientists like Niels Bohr and Max Born, who had already begun to challenge the idea that particles could be precisely located and their velocities perfectly known. What Heisenberg proposed was that at the quantum level, it was fundamentally impossible to know both the position and the momentum of a particle with absolute certainty. In classical physics, the idea of uncertainty did not exist. If you could measure the position of an object, you could also measure its velocity, and you could predict its future position. However, Heisenberg's uncertainty principle showed that in the microscopic world of atoms and particles, these concepts no longer applied. The more precisely one measured the position of a particle, the less precisely its momentum could be known, and vice versa. This discovery shattered the deterministic outlook of classical physics, where it was believed that the complete knowledge of a system would allow for precise predictions of its behavior. In Heisenberg's new world, uncertainty was not a limitation of measurement tools, but an inherent feature of the universe itself. The implications of Heisenberg's uncertainty principle went beyond the technicalities of quantum mechanics. His work suggested that nature, at its most fundamental level, did not follow the strict rules of classical physics. Instead of certainty, nature was governed by probability. Rather than being able to predict with accuracy the exact path of a particle, scientists could only predict the likelihood of its position or momentum. The universe, at its core, was not deterministic, it was probabilistic. This was a profound shift in how scientists and philosophers thought about the world. If uncertainty could not be avoided at the quantum level, what did this mean for our understanding of the universe? Was everything subject to the same probabilistic rules? Or was this uncertainty limited to the microscopic world? The implications of Heisenberg's discovery were far-reaching, not only in science, but in philosophy, as it called into question the very nature of reality. What became clear was that the universe at the quantum level was not a well-oiled machine where every movement could be predicted, but rather a dynamic, uncertain system where only probabilities governed the outcomes of events. Heisenberg's breakthrough did not immediately gain universal acceptance. Many scientists struggled to come to terms with the philosophical consequences of his uncertainty principle. If the future could not be predicted with certainty, what did that mean for our ability to understand and control the world around us? How did this new understanding fit with our everyday experiences, where we still operated in a world that seemed, for the most part, to follow deterministic laws? The quantum revolution sparked by Heisenberg's uncertainty principle opened the door to new theories and new ways of thinking about the universe. It led to the development of quantum mechanics, a field that would later produce remarkable technologies such as lasers, transistors, and MRI scanners. It also fueled debates in the philosophy of science, as thinkers such as Niels Bohr, Albert Einstein, and Erwin Schrödinger grappled with the implications of Heisenberg's ideas. While some embraced the uncertainty inherent in quantum mechanics, others, like Einstein, famously resisted the idea, famously saying, "God does not play dice with the universe." In the years that followed, quantum mechanics continued to develop, and Heisenberg's uncertainty principle became a cornerstone of modern physics. Despite the initial resistance, the principle was confirmed through numerous experiments and became a fundamental aspect of our understanding of the atomic world. Today, Heisenberg's breakthrough remains one of the most important and revolutionary discoveries in science, as it forever altered our perception of the universe and our place within it. As we continue to explore the implications of quantum mechanics, we are reminded of the immense complexity and mystery of the universe. Heisenberg's uncertainty principle shattered the once unwavering belief in a certain and deterministic universe, revealing a world that is far more unpredictable and probabilistic than we could have ever imagined. It is a reminder that science is not about discovering ultimate certainty, but about exploring the unknown and embracing the mysteries that lie beyond our understanding. In the world of quantum mechanics, uncertainty is not an obstacle. It is an integral part of the fabric of reality itself. Heisenberg's uncertainty principle did not merely disrupt the physical understanding of particles and matter at the quantum level. It catalyzed a paradigm shift that extended far beyond the confines of the scientific community, stirring deep philosophical questions about the nature of reality itself. To grasp the magnitude of Heisenberg's contribution, it is essential to examine how this breakthrough fundamentally altered our approach to physics and, in turn, reshaped our conception of knowledge, determinism, and the very possibility of certainty in science. Before Heisenberg's revelation, the classical worldview maintained a reassuring certainty about the nature of the universe. Based on Newtonian physics, the laws of motion and gravitation dictated a universe where, if one could know all the forces at work in a given system, one could predict future events with perfect accuracy. The determinism inherent in classical physics was foundational to the scientific revolution. It suggested that everything, from the smallest atom to the largest celestial bodies, could be understood and predicted if enough data was available. This perspective aligned with the Enlightenment ideals of rationality and the power of human reason to uncover the truths of the natural world. However, as quantum mechanics began to emerge in the early 20th century, this certainty began to unravel. The study of atomic and subatomic particles revealed behavior that defied the neat, predictable patterns established by classical physics. The electron, for example, could not be pinned down with absolute accuracy in terms of both position and velocity at the same time. This observation led Heisenberg to formulate his uncertainty principle, which proposed that the more precisely one measures the position of a particle, the less precisely one can know its momentum, and vice versa. In essence, the very act of measurement itself became an inseparable part of the system, introduced an inherent fuzziness into the understanding of particles and their behaviors. The implications of Heisenberg's principle went beyond the realm of quantum mechanics and entered into deep philosophical territory. For centuries, the scientific method had been based on the belief that reality could be understood through observation, measurement, and calculation. Heisenberg's principle, however, called into question whether this was truly possible. If absolute certainty was impossible in the quantum realm, could it ever be attained in any domain of science? And what did this uncertainty mean for the concept of knowledge itself? The idea that the future of particles and potentially all events could not be precisely predicted raised new questions about determinism and free will. This shift also had profound implications for our understanding of the nature of reality. Classical physics had operated on the assumption that the universe was like a machine working according to fixed and predictable laws. Heisenberg's uncertainty principle, however, introduced a concept that was much more fluid and probabilistic. At the quantum level, particles did not have definite positions or velocities until they were measured. Until that point, their properties existed only in terms of probabilities. This view suggested that reality was not a set of objective facts waiting to be uncovered, but rather a dynamic and probabilistic field that required interaction to give it form. The observer, through measurement, played an active role in shaping the state of the system. In a sense, the universe became something much less rigid and much more fluid, where outcomes could only be expressed in terms of likelihoods rather than certainties. This concept also had significant repercussions for the philosophy of science. In the early 20th century, the scientific community was still firmly embedded in a belief in objective, observable truths. Heisenberg's work, however, suggested that the very nature of observation could influence the outcome of an experiment, challenging the notion of objective reality that had been a cornerstone of the scientific worldview. The implications were profound, as they raised the possibility that no matter how sophisticated our instruments or techniques might become, there would always be limits to our knowledge of the universe. The idea of objective reality, where things exist independently of our perceptions or observations, was called into question. Heisenberg's discovery also led to new debates about the role of human perception in understanding the universe. If reality at the quantum level could not be fully known, then how could human beings ever claim to have a true understanding of the universe? Was all knowledge necessarily limited and incomplete? Philosophers like Niels Bohr, who worked closely with Heisenberg, contended that the uncertainty principle did not imply that reality was inherently unknowable, but rather that we needed to rethink the nature of knowledge itself. Bohr suggested that the language of classical physics was no longer sufficient to describe the quantum world and that new ways of thinking and speaking about the universe were necessary. Thus, Heisenberg's work not only altered the methods of scientific inquiry, but also encouraged a re-evaluation of the philosophy behind the scientific method. Heisenberg's uncertainty principle led to the creation of the Copenhagen interpretation of quantum mechanics, which was based on the idea that particles do not have definite properties until they are observed. This interpretation was controversial because it implied that the act of observation was integral to the reality of particles, further complicating the classical idea of an objective, independent universe. The Copenhagen interpretation posited that the universe was not deterministic but probabilistic, where only the probabilities of different outcomes could be predicted. This, in turn, raised important questions about the role of human consciousness in the creation of reality. As Heisenberg's theory gained acceptance in the scientific community, it opened the door to a range of new technologies and applications. One of the most notable results of quantum mechanics powered in part by Heisenberg's uncertainty principle, was the development of quantum computing. Quantum computers, unlike classical computers, use the principles of superposition and entanglement to perform calculations in ways that classical computers cannot. This could revolutionize fields such as cryptography, medicine, and artificial intelligence, allowing for computations that were previously thought to be impossible. However, quantum mechanics, with its inherent uncertainty, also creates challenges in the development of these technologies, as the unpredictability of quantum systems remains a hurdle that scientists continue to work to overcome. In the decades following Heisenberg's breakthrough, the implications of his work continued to unfold, not only within physics but also within the broader culture. The idea that the universe was fundamentally uncertain and that the future could not be predicted with absolute certainty began to resonate with other disciplines. In literature, philosophy, and the arts, the acceptance of uncertainty and randomness as inherent elements of reality influenced a generation of thinkers, writers, and artists. The works of authors like Franz Kafka, who explored themes of uncertainty and the search for meaning in an indifferent universe, echoed the implications of Heisenberg's scientific discoveries. Furthermore, Heisenberg's work also influenced modern views on the nature of human existence. If the universe was inherently uncertain, then perhaps the human experience itself was not one of predestination or deterministic outcomes, but one shaped by the random events and choices we make. In this sense, Heisenberg's uncertainty principle became a metaphor for life itself, a reminder that, despite our best efforts to control and predict our futures, there will always be a degree of unpredictability in the outcomes we face. In conclusion, Werner Heisenberg's uncertainty principle not only shattered the certainty that had long defined classical physics, but also introduced a new way of thinking about the universe and the nature of reality. His breakthrough was a pivotal moment in the history of science, ushering in the era of quantum mechanics and redefining how we view knowledge, observation, and the limits of human understanding. As we continue to explore the implications of Heisenberg's discovery, it remains a testament to the complexity of the universe and the enduring quest for knowledge, a reminder that even in the face of uncertainty, science continues to push the boundaries of what we know and understand. The Heisenberg uncertainty principle's implications extend far beyond the realm of physics and into the heart of philosophy, culture, and even our everyday experience of reality. To truly understand the magnitude of Werner Heisenberg's breakthrough and its subsequent impact, it is essential to delve into the second keynote, the uncertainty principle's challenge to determinism. This is not only a physical law, but a profound shift in how we approach knowledge, existence, and the inherent unpredictability of the universe. Before Heisenberg's uncertainty principle, the dominant worldview in science was rooted in determinism. Determinism, at its core, posits that every event or state of affairs, including human actions, is the outcome of preceding events, governed by laws that are as fixed and unalterable as the laws of nature themselves. This deterministic view, epitomized by Newtonian physics, suggested that if we had perfect knowledge of the forces acting on a system, we could predict the future with certainty. Classical mechanics, with its structured equations of motion, assumed that every aspect of an object's movement was knowable and predictable, given the right conditions. The belief in this kind of certainty allowed humans to feel as though they could control or understand the world through measurement and calculation. The universe was seen as a grand machine, ticking along according to immutable laws. This deterministic mindset was reinforced by the success of classical physics in explaining the motion of planets, the behavior of everyday objects, and the functioning of machines. Newton's laws of motion, for example, seemed to provide the blueprint for understanding everything from the trajectory of a thrown ball to the movement of the stars. In this world, knowledge was power, and by observing, measuring, and calculating, humanity could foresee the future. At its heart, classical physics suggested that, with enough precision, everything could be predicted. But the advent of quantum mechanics and, more specifically, Heisenberg's uncertainty principle, upended this worldview. The uncertainty principle, which asserts that one cannot simultaneously know both the exact position and the exact momentum of a particle with perfect accuracy, directly contradicts the idea that a complete knowledge of the system leads to a precise prediction. This means that in the quantum world the certainty of classical physics gives way to a probabilistic model. The outcomes of quantum experiments are not predictable with certainty, only in terms of probabilities. This idea profoundly challenges the very foundation of classical physics, the belief that the universe operates like a giant clockwork mechanism. According to classical physics, every particle had a definite position and velocity at any given moment, and it was simply a matter of calculating those values to predict future states. In stark contrast, quantum mechanics and the uncertainty principle reveal that some aspects of a system could not be known exactly, no matter how advanced our instruments or methods became. This revelation shattered the comforting certainty that classical physics had offered. In a sense, the universe was no longer a clock ticking away predictably. Instead, it became a probabilistic system where the future could never be fully known. The implications of this shift were far-reaching, extending beyond the confines of physics into the realm of philosophy. One of the most fundamental assumptions of classical thinking was the idea of causality, the belief that every effect had a specific cause, and that cause could be determined through observation and reason. This idea of a cause and effect chain running through the universe aligned with the deterministic view, which posited that, given enough knowledge, every event could be traced back to its origin. Heisenberg's uncertainty principle called this belief into question. If the exact state of a system cannot be known with certainty, how can we be sure of its cause? This challenge to determinism implied that causality, in the strict classical sense, might not hold in the quantum world. At the microscopic level, the universe no longer adhered to a rigid, linear cause and effect relationship. Instead, particles existed in states of probability, and their behaviors were influenced by waves of potentiality rather than fixed causes. This challenge to determinism also raised profound questions about the nature of free will. If the future could not be predicted with certainty, then could human behavior also be subject to the same unpredictability? The classical view of free will had been predicated on the belief that individuals could make choices that would lead to specific, predictable outcomes based on the laws of nature. However, if the future is probabilistic, then the very notion of free will could be viewed as equally uncertain. This uncertainty opened up new philosophical discussions about human autonomy and the nature of choice, pushing thinkers to reconsider whether free will was an illusion, or whether it operated in a more complex, probabilistic manner. Furthermore, the uncertainty principle's rejection of determinism had broader implications for the scientific community and its pursuit of knowledge. Throughout the 19th century, science had advanced with the belief that, given enough time and resources, everything could eventually be known. This optimism was encapsulated in the concept of a complete theory, a unified understanding of the laws of nature that could explain all phenomena, from the motion of celestial bodies to the behavior of subatomic particles. The expectation was that science would gradually uncover the laws governing everything, reducing the unknown to the known, and eradicating uncertainty. But Heisenberg's work shattered this vision. By introducing the idea that certain aspects of reality were fundamentally unknowable, Heisenberg challenged the notion that science could ever reach a final, all-encompassing theory. The inherent uncertainty of the quantum world suggested that science would always be constrained by limits, and that there would always be a gap between what we could know and what actually existed. In a sense, Heisenberg's uncertainty principle not only revolutionized physics but also changed the way scientists viewed the very project of scientific inquiry. Instead of seeking absolute certainty, scientists had to come to terms with a world in which uncertainty was a permanent feature of existence. This shift also had profound consequences for how scientists approached the study of nature. In the pre-quantum world, the goal of scientific experimentation was to observe and measure, in order to determine the exact state of a system and predict its future behavior. In the quantum world, however, measurement itself became a central issue. The act of observing a quantum system could influence its state, making it impossible to separate the observer from the observed. This meant that in quantum experiments, the distinction between subject and object, observer and observed, became blurred. The uncertainty principle highlighted the limits of human knowledge, reminding scientists that observation itself was a deeply interactive process, one that altered the very nature of the system being studied. The idea of probabilistic outcomes, rather than deterministic ones, also permeated other areas of physics. For example, The behavior of atoms and molecules in chemical reactions, once thought to be predictable through classical mechanics, was now understood to be governed by quantum principles. The behavior of electrons within an atom was no longer viewed as following a clear, deterministic path. Instead, their positions and movements could only be understood in terms of probability, and the exact behavior of a system could never be fully known. This required scientists to rethink their approach to the study of matter, shifting away from the idea of deterministic forces and toward a focus on probability distributions and statistical mechanics. As the uncertainty principle began to take root, it sparked a fundamental rethink of the role of human agency and perception in the shaping of reality. The observer was no longer an impartial witness to an objective reality, but an active participant in the creation of that reality. This blurred the lines between subjectivity and objectivity, raising questions about the relationship between the mind and the physical world. In many ways, the uncertainty principle and its associated concepts open the door to a more interactive, subjective view of the universe, one in which knowledge was not something to be extracted from the world, but something that was co-created through observation. In conclusion, Heisenberg's uncertainty principle not only challenged the determinism that had been central to classical physics, but also transformed our understanding of knowledge, reality, and the role of human perception in shaping the world. The implications of this principle stretched far beyond the field of physics, influencing everything from philosophy to the way we think about free will and human agency. The probabilistic nature of quantum mechanics, revealed by Heisenberg's work, replaced the deterministic worldview with one in which uncertainty was not an anomaly, but a defining characteristic of the universe. This shift, while unsettling, opened up new possibilities for the way we understand the nature of existence, forcing us to confront the limits of our knowledge and embrace a universe that is, at its core, uncertain. In the evolution of modern physics, the development of quantum mechanics has been a transformative milestone, and at the heart of this transformation lies the Heisenberg uncertainty principle. This principle, introduced by Werner Heisenberg in 1927, represents one of the most profound departures from classical physics and challenges the deterministic worldview that had dominated scientific thought for centuries. It undermines the very foundation of Newtonian mechanics, which had instilled a belief in the predictability of the universe. The second keynote in Heisenberg's revolutionary shift in understanding is uncertainty principle's impact on the nature of knowledge and the epistemology of science. Understanding this keynote means confronting the epistemological implications of quantum mechanics and exploring how Heisenberg's insight reshaped the philosophy of science, our understanding of knowledge, and the boundaries of human understanding. To appreciate the magnitude of Heisenberg's impact on the philosophy of science, it is important to first understand the philosophical underpinnings of classical physics. Classical mechanics, based on the principles laid out by Isaac Newton, was founded on a belief in determinism and the possibility of absolute knowledge. Under classical physics, scientists operated under the assumption that the universe was comprehensible, predictable, and knowable. It was thought that, through observation, measurement, and calculation, human beings could come to a precise understanding of the laws governing the physical world. The worldview, deeply rooted in Enlightenment ideals, suggested that the objective universe could be understood through a detached, rational examination, and that human reason could uncover its deepest secrets. This classical framework rested on a certain epistemological assumption, the belief that knowledge could be absolute and objective. In the classical world, there was little room for the possibility that the limitation of human measurement and observation could hinder the pursuit of knowledge. It was assumed that with enough precision and advanced instruments, humans could come closer to grasping the fundamental truths of the universe. In fact, the concept of scientific progress was, to a large extent, tied to the idea of increasing precision and reducing uncertainty. As science advanced, it was believed certainty in knowledge would follow. However, when Heisenberg introduced his uncertainty principle, he shattered this belief. The very act of measuring, according to Heisenberg, creates an inherent uncertainty in the system being studied. The uncertainty principle posits that there is a limit to how precisely we can simultaneously measure certain pairs of properties of a particle, most notably its position and momentum. The more accurately one of these quantities is measured, the less accurately the other can be known. This concept challenges the classical assumption that measurements can be made without affecting the system being observed. Heisenberg's principle did not merely represent a technical limitation. It signified a fundamental constraint in the nature of reality itself. The epistemological impact of the uncertainty principle is far-reaching. For one, it directly challenges the notion of objective knowledge. Classical physics adhered to the belief that the universe existed independently of all observations, and that, through careful measurement, we could uncover its truths. Heisenberg, however, pointed out that at the quantum level, the observer and the observed were inextricably linked. The very act of observing or measuring a particle affected its state, making it impossible to fully separate the two. In this sense, Heisenberg's uncertainty principle suggests that objective knowledge, at least in the quantum realm, is an illusion. Knowledge is not an impartial reflection of an objective reality. It is intrinsically linked to the act of observation. Prior to Heisenberg's work, the prevailing scientific worldview was that knowledge could ultimately be absolute, or at least that with enough data and observation, one could reduce the error in measurements to an arbitrarily small amount. The idea was that, in principle, everything could be known with enough precision. Heisenberg's uncertainty principle fundamentally undermines this assumption. By asserting that there are inherent limits to what can be known, this introduces a paradigm shift in how we understand knowledge itself. The very nature of uncertainty, as expressed in the uncertainty principle, reveals that there are elements of reality that remain unknowable not because of technological limitations, but because they are intrinsically uncertain. This challenges the idea that the universe is governed by predictable laws that we can ultimately understand. In the quantum realm, certainty is replaced by probability, and the universe is not deterministic in the classical sense. Instead of a universe where the future is a logical extension of the past, quantum mechanics presents a world where only probabilities govern outcomes. This realization has philosophical consequences that extend far beyond the boundaries of physics. By introducing uncertainty as a fundamental feature of nature, Heisenberg also complicated the relationship between knowledge and truth. In classical physics, knowledge was considered the path to uncovering the ultimate truth about the universe. With Heisenberg's work, however, the pursuit of knowledge became more complicated, as it required scientists to accept the inherent limitations of their tools, their methods, and their observation. This epistemological shift was not simply technical but philosophical. The certainty that had been central to the scientific method was no longer an achievable goal. Instead, the scientist had to come to terms with a world where knowledge was probabilistic, uncertain, and limited by the very nature of measurement. Another profound epistemological consequence of Heisenberg's work lies in the relationship between the observer and the observed. Classical physics, rooted in the scientific method developed during the Enlightenment, assumed that the scientist could observe the universe without altering it. The observer was assumed to be a detached, neutral figure, capable of studying the world without influencing it. However, Heisenberg's uncertainty principle shatters this assumption. According to quantum mechanics, the act of observing a quantum system changes its state. In other words, the observer is no longer a passive entity. Instead, the observer actively participates in shaping the state of the system being studied. This realization has profound implications for how we think about objectivity. In classical science, objectivity was achieved by eliminating any influence the observer might have on the system. But in the quantum realm, objectivity becomes a more complex concept. If the very act of observation changes the system, can we ever truly know an objective reality? Heisenberg's work suggests that the observer and the observed cannot be separated, and the process of observation becomes part of the reality itself. This has led to debates in both physics and philosophy about the limits of human knowledge, the role of the observer, and the nature of objectivity in science. The uncertainty principle, thus, introduces a new form of objectivity, one that is not based on absolute detachment but on the acceptance of our limitations as observers. The uncertainty of quantum mechanics, in this sense, becomes a new form of scientific realism where scientists acknowledge that they can only ever know the probabilities of events, not certainties. This new approach to objectivity requires a rethinking of how we approach science, knowledge, and truth. While Heisenberg's uncertainty principle originated within the field of quantum mechanics, its implications stretch far beyond physics. The idea that the universe is inherently uncertain and that knowledge is limited has resonated in a variety of disciplines, including philosophy, literature, and even psychology. In philosophy, thinkers such as Niels Bohr and Albert Einstein engaged with the epistemological consequences of Heisenberg's work, considering what it meant for our understanding of reality. Bohr famously proposed that the uncertainty principle didn't imply that the universe was unknowable, but rather that we needed to rethink how we understand knowledge. In literature, the uncertainty and the blurred boundaries between subject and object have been explored by writers grappling with the complexities of human perception and the nature of reality. In psychology, the principle has resonated with the understanding that human perception itself is inherently limited, and that our understanding of the world is shaped not just by observation, but by our inherent cognitive biases and limitations. These disciplines, too, have been forced to confront the question of what can be known and how uncertainty shapes our experience of the world. The lasting impact of Heisenberg's uncertainty principle, however, lies in the way it has influenced not only the scientific community, but also the way we think about science itself. The principle has forced us to reconsider the relationship between knowledge and reality. It has exposed the limits of human understanding and revealed that some aspects of the universe will always remain beyond our reach. While this uncertainty can be unsettling, it has also opened up new avenues for scientific inquiry, forcing scientists to think more deeply about the role of observation, measurement, and the relationship between the observer and the system being studied. In conclusion, Heisenberg's uncertainty principle did not just revolutionize physics, it revolutionized the way we think about knowledge, objectivity, and the nature of reality itself. It challenged the determinism and absolute certainty of classical physics, introducing a new, probabilistic view of the universe. At the same time, it raised profound epistemological questions about the limits of human understanding and the relationship between the observer and the observed. The uncertainty that Heisenberg introduced was not just a technical challenge to classic physics, but a philosophical rethinking of the very nature of science and knowledge. Today, Heisenberg's legacy continues to shape both the scientific community and the broader cultural landscape, reminding us that uncertainty is not a flaw in our knowledge but a fundamental feature of the universe itself. Werner Heisenberg's uncertainty principle remains one of the most revolutionary concepts in the history of science. It dramatically altered not only the field of quantum mechanics but also the broader understanding of the universe. While the first and second keynotes focused on the challenge to determinism and the epistemological shift in knowledge, the third keynote is equally transformative in nature. This keynote emphasizes the philosophical implications of the uncertainty principle, particularly its impact on our understanding of reality, objectivity, and human perception. It is not just a technical detail of physics, but a concept that reshapes how we view the nature of existence itself. In classical physics, the universe was understood as a vast machine, mechanistic, predictable, and governed by strict laws. Every particle and every event in the universe operated in a deterministic manner. This classical view, solidified by the work of Isaac Newton and others, suggested that by knowing the current state of a system, that is the position and velocity of a particle, one could precisely calculate its future state. The belief was that the universe was fully knowable, and that certainty could be achieved through measurement. There was little room in this worldview for any kind of doubt or uncertainty. Classical physics, for all its beauty and success in explaining macroscopic phenomena, was rooted in the belief that reality could be fully comprehended if observed and measured correctly. This worldview, however, was shattered by the development of quantum mechanics. At the quantum scale, the laws of classical physics no longer held. Electrons, photons, and other subatomic particles were found to exhibit behaviors that could not be predicted with the same precision as larger objects. Instead of moving in smooth, predictable paths, quantum particles seemed to exist in a state of probability, where their position and momentum could only be known in terms of likelihoods. This probabilistic nature of subatomic particles was epitomized by Heisenberg's uncertainty principle. It essentially states that there are fundamental limits to the accuracy with which certain pairs of physical properties like the position and momentum of a particle can be measured simultaneously. The more precisely we measure one, the less precisely we can know the other. This was a fundamental departure from classical physics, where it was assumed that every quantity could be measured and known with precision. At first glance, the uncertainty principle might seem like a minor technical limitation, a byproduct of experimental imperfection. But Heisenberg's discovery, with its profound philosophical implication, points to something much deeper about the nature of reality. If the exact position and momentum of a particle cannot be known at the same time, does that mean the very nature of the particle is uncertain? Can we truly know what the universe is like at its most fundamental level? Or is there an inherent indeterminacy built into the fabric of reality? These questions touch on some of the oldest and deepest issues in philosophy: the relationship between the observer and the observed, the nature of objective reality, and the limits of human knowledge. The implications of Heisenberg's work extend far beyond the confines of quantum physics. They raise profound philosophical questions about objectivity and perception. Classical physics, with its deterministic laws, suggested that the universe was like a giant machine running according to fixed rules. In this worldview, the observer was seen as an external agent who could observe the world without influencing it. The universe existed independently of human consciousness. But quantum mechanics, as Heisenberg's uncertainty principle suggests, introduces the idea that observation is not a neutral, passive process. The very act of observing a quantum system changes the system, meaning the observer and the observed are inextricably linked. This realization has profound consequences for our understanding of objectivity. In classical science, objectivity was thought to be achieved by eliminating any influence the observer might have on the system being studied. The observer was a detached figure, observing without affecting. However, Heisenberg's uncertainty principle shows that at the quantum level, this is not possible. The act of measurement itself influences the system being measured. This blurs the boundary between subject and object, suggesting that objectivity is not an absolute state, but rather a dynamic relationship between the observer and the observed. This challenges the classical notion of a purely objective, independent reality that exists apart from human perception. Instead, Heisenberg's work invites us to reconsider the nature of observation and knowledge. Moreover, the uncertainty principle leads us to a more fluid and interconnected view of reality. In the classical worldview, the universe was a machine composed of separate, distinguishable parts, each governed by its own predictable laws. In contrast, the quantum view of the universe suggested by Heisenberg's uncertainty principle paints a much different picture, one where the observer, the measured system, and the act of measurement all participate in the shaping of reality. This interconnectedness challenges the old mechanistic view and suggests that reality is not a fixed, independent structure, but rather a dynamic process that is constantly shaped by the interaction of observation and measurement. This idea that reality is probabilistic rather than deterministic is a significant departure from the way the world was understood in classical physics. It introduces an element of chance and unpredictability at the very heart of the universe. In the quantum world, particles do not exist in one definite state, but rather exist in a superposition of possible states, and only when observed do they collapse into a specific state. This is a fundamentally different way of thinking about reality. It suggests that the universe does not operate like a well-oiled machine, where every detail can be predicted. Instead, it operates more like a field of possibilities, where outcomes are governed by probabilities. Heisenberg's uncertainty principle forces us to confront the limits of human knowledge. In classical physics, there was an implicit belief that, with enough observation and precision, we could uncover the fundamental truths of the universe. The uncertainty principle, however, shows that there are limits to what we can know. Some aspects of reality will always remain uncertain, not because of technological limitations, but because uncertainty is built into the fabric of nature itself. This means that there will always be a gap between what is observed and the complete objective reality. This is a humbling realization for those who believe in the boundless power of human reason and observation. The implications of this uncertainty extend to other areas of human inquiry as well. In philosophy, the uncertainty principle has sparked debates about the nature of knowledge, perception, and reality. Thinkers like Niels Bohr, who worked closely with Heisenberg, grappled with the idea that knowledge was never fully objective or complete. Instead, They proposed that knowledge was inherently limited by the act of observation and that reality itself was not something that could be objectively known but something that was always shaped by the relationship between the observer and the observed. This notion of uncertainty also has applications in the human sciences. In psychology, for example, the uncertainty principle suggests that human perception is inherently limited. We can never fully know the world in its entirety because we are always interacting with it through our own subjective lens. Similarly, in the social sciences, the principle raises questions about the possibility of objective knowledge of human behavior. Can we truly understand human society and behavior with the same certainty that classical physics once promised, or are our theories and observations of the social world subject to the same kind of uncertainty that quantum mechanics reveals in the physical world? Moreover, the uncertainty principle invites us to rethink the role of free will and human agency. Classical physics, with its deterministic view, suggested that all events, including human actions, were the result of prior causes and could be predicted with sufficient knowledge. In contrast, the probabilistic nature of quantum mechanics implies that not everything is predetermined. The outcomes of quantum events are not fixed, but are probabilistic. This idea has resonated with some philosophers who argue that just as the quantum world is uncertain, so too is human behavior. The human experience, much like the universe, may be characterized by unpredictability and chance rather than rigid determinism. Finally, Heisenberg's uncertainty principle has had a lasting impact on the development of technology. While its philosophical and epistemological implications have been profound, its practical applications have been equally transformative. Quantum mechanics, with its probabilistic approach to understanding particles, has led to the development of technologies such as quantum computing, which relies on the strange properties of quantum particles. These technologies, which once seemed like science fiction, are now on the cusp of revolutionizing fields such as cryptography, artificial intelligence, and computing. The uncertainty principle, while suggesting limits to our knowledge, also open the door to new kinds of scientific inquiry and technological innovation. In conclusion, Heisenberg's uncertainty principle is not just a fundamental concept in quantum mechanics, it is a key to understanding the very nature of knowledge and reality. It forces us to confront the limits of human perception, the relationship between the observer and the observed, and the uncertainty that underlies the universe. It challenges the classical worldview of a deterministic, predictable universe, and replaces it with a probabilistic and interconnected reality. Heisenberg's breakthrough has profound philosophical and scientific implications that continue to shape our understanding of the world today. Through it, we come to realize that uncertainty is not just a flaw in our measurements, it is an inherent feature of the universe itself. The uncertainty principle is a reminder that, in the quest for knowledge, there will always be limits, and the universe will forever remain a place of mystery and wonder. Heisenberg's uncertainty principle, while groundbreaking in its revolution of the scientific understanding of the quantum world, carries far-reaching implications that extend well beyond the boundaries of physics. It challenges not only the deterministic outlook of classical physics, but also the very structure of knowledge itself. As we explore the third keynote, the impact of the uncertainty principle on the perception of reality and human knowledge, we delve into how Heisenberg's insight transformed our views on what we can know, how we perceive the universe, and the very fabric of the nature of reality itself. In classical physics, the understanding of the universe was dominated by the idea of an objective, predictable reality. Classical mechanics, grounded in the work of Isaac Newton, built a framework that saw the universe as a vast machine operating according to immutable laws. The position, velocity, and forces governing objects could be known precisely, and as a result, the future could be predicted with great accuracy. This was the view that dominated scientific thought for centuries, and it promised that, with sufficient knowledge and tools, humans could uncover the ultimate truths about the world around them. The laws of nature were thought to be set in stone, absolute, and universally applicable. If we could observe the world and measure its components accurately, the world would unfold like a predictable story. Heisenberg's uncertainty principle disrupted this comforting belief by showing that, at the most fundamental level of reality, this certainty and predictability were not guaranteed. The principle asserts that it is impossible to simultaneously know both the position and the momentum of a particle with complete precision. The more precisely we measure one of these properties, the less precisely we can measure the other. This idea went against everything that classical physics held dear. It suggested that at the quantum scale there were limits to the precision with which we could understand the state of a system. It was no longer possible to determine every aspect of the system's behavior in the way that classical physics promised. The implications of this were far-reaching. If we could no longer rely on the idea that the universe followed deterministic laws in all cases, how could we trust that the world we experience is truly knowable? Heisenberg's uncertainty principle forced scientists to confront the fact that some aspects of reality were inherently unknowable. This was not due to the limitations of measurement tools or a lack of data, but because there were fundamental constraints on what could be known about certain systems. This realization shattered the notion that the universe at its core was a predictable machine operating according to fixed laws. Instead, it suggested a universe that was inherently probabilistic, where outcome could be described only in terms of likelihoods rather than certainties. This new understanding of the universe raised significant philosophical questions about the nature of reality itself. If the position and momentum of a particle could never be precisely known at the same time, did that mean that reality itself was inherently uncertain? Heisenberg's uncertainty principle invited scientists and philosophers alike to reconsider the assumption that the world exists independently of our observation and understanding. In classical physics, the assumption was that the universe operated independently of the observer. The observer, whether a human or an instrument, was seen as a detached entity that could measure and understand the world without affecting it. But Heisenberg's work pointed out that at the quantum level, the observer could not be separated from the observed. The act of measurement fundamentally altered the state of the system being observed. This blurring of the lines between subject and object suggested that reality was not a fixed, external entity, but something that was intertwined with the observer. This shift in perspective had significant implications for how we understand knowledge itself. For centuries, knowledge had been conceptualized as a process uncovering objective truths about the world. It was assumed that, with enough observation, measurement, and reasoning, we could discern the true nature of reality. Heisenberg's uncertainty principle, however, introduced a profound challenge to this assumption. If the universe could not be fully known, what did it mean to have knowledge of the world? Knowledge was no longer an absolute and unchanging reflection of reality, but became something inherently limited and conditional. This realization pushed philosophers to rethink what it meant to know something and whether true objectivity was ever truly attainable. The uncertainty principle also forced a reconsideration of the relationship between science and the human experience. In the classical view, science was the tool through which humans could gain access to objective reality, stripping away the subjectivity of human perception. However, the uncertainty principle, by showing the limitations of our ability to measure and observe, suggested that science itself was not as objective as it had been portrayed. Knowledge, in this new framework, became something more fluid, subjective, and uncertain. The boundaries between the observer and the observed were no longer as clear, and the scientific method was no longer the simple process of discovering objective truths about an independent reality. Instead, science became a complex and nuanced process of interacting with the world in ways that were inevitably influenced by the limitations of our tools and our perception. This shift has had lasting effects not only in physics but in other disciplines as well. In the realm of philosophy, the uncertainty principle has led to debate about the nature of truth and the limits of human knowledge. Philosophers such as Niels Bohr, who was deeply involved in the development of quantum mechanics, embraced the idea that uncertainty was not a flaw of measurement but an intrinsic part of reality. Bohr proposed that the uncertainty in quantum mechanics was not a sign of failure but a reflection of the nature of the quantum world. This view challenged the classical idea that truth could be found by peeling away the layers of observation to reveal the objective reality underneath. Instead, truth in the quantum world became something that was relative, probabilistic, and dependent on the context of observation. In addition to its impact on philosophy, the uncertainty principle has also influenced the arts and culture. The idea that reality is not fixed and that outcomes are uncertain has found expression in literature, art, and film. Writers and artists have explored themes of uncertainty, subjectivity, and the limits of human understanding, reflecting the changing views of reality brought about by quantum mechanics. Works of literature that explore the fluidity of time, the fragmentation of identity, and the uncertainty of existence resonate with the ideas introduced by Heisenberg's discovery. In film, stories of alternate realities, parallel universes, and the malleability of time echo the uncertainty principle's suggestion that the universe is not a fixed, knowable entity but something that is dynamic and subject to change depending on the perspective of the observer. The uncertainty principle has also had a profound effect on modern technology. While its philosophical implications are immense, its practical applications are equally significant. The development of quantum technologies, such as quantum computers and quantum cryptography, has been made possible by the understanding of quantum mechanics and the probabilistic nature of quantum particles. Quantum computers, for example, exploit the superposition and entanglement of quantum particles to perform calculations that would be impossible for classical computers. These advances, while exciting, also highlight the limits of our knowledge. The inherent uncertainty in quantum systems must be accounted for when designing and building quantum technologies, as it introduces complexities that are absent from classical systems. One of the most remarkable aspects of Heisenberg's uncertainty principle is that it continues to shape the way we think about science and the universe even today. While we may have grown accustomed to the idea that certain outcomes are probabilistic, the concept of uncertainty still challenges our sense of control and certainty. The world we inhabit is not one of absolute laws and fixed outcomes, but a world in which probability governs the behavior of particles and the very structure of reality. Heisenberg's discovery reminds us that the universe is far more complex and mysterious than we once imagined. It is a universe that resists simple understanding, and in this resistance, it reveals the inherent limitations of human knowledge. In conclusion, Heisenberg's uncertainty principle fundamentally reshaped not only the scientific understanding of the quantum world but also the philosophical underpinnings of knowledge itself. It forced scientists, philosophers, and thinkers in every discipline to confront the limits of human understanding and the fluid, probabilistic nature of reality. Heisenberg's insight changed the way we perceive the universe, replacing the deterministic certainty of classical physics with a world governed by uncertainty and probability. This shift in perspective has not only revolutionized physics but has also influenced philosophy, art, and culture, reminding us that the pursuit of knowledge is an ongoing process, forever constrained by the inherent uncertainties of the universe. Heisenberg's uncertainty principle, which states that one cannot simultaneously know both the exact position and momentum of a particle, had a profound impact on the understanding of the quantum world and the very nature of scientific knowledge. The principle posed significant challenges to classical physics and its deterministic view of the universe. The shift to a probabilistic model of reality not only changed the field of physics, but also influenced how humans perceive reality itself. Classical physics, which dominated scientific thought for centuries, was built on the assumption that the universe operated like a machine governed by precise, predictable laws. Under this view, if you had enough information about the current state of a system, such as the position and velocity of a particle, you could predict its future behavior with certainty. This deterministic outlook was a hallmark of Newtonian mechanics, where the future was always seen as a logical extension of the past, governed by the laws of nature. Classical physics offered a sense of control and predictability, suggesting that if we could measure everything accurately, we could unlock the mysteries of the universe. However, Heisenberg's uncertainty principle shattered this certainty. It revealed that at the quantum level, there were fundamental limits to what could be known. For particles, the more precisely you measure one property, such as position, the less precisely you can know another, such as momentum. This intrinsic uncertainty was not due to limitations in measurement technology but was inherent in the very nature of quantum systems. Heisenberg's work suggested that the quantum world operates according to probabilities rather than certainties. Rather than being able to predict exact outcomes, quantum mechanics could only provide the likelihood of certain events occurring. This shift from a deterministic to a probabilistic model was one of the most profound changes in the history of science. The uncertainty principle also had significant philosophical implications, particularly concerning the nature of knowledge and reality. In classical physics, it was assumed that the universe existed independently of our observation and could be understood through detached, objective observation. The act of measurement in classical physics was seen as something that could be done without affecting the system. However, in the quantum realm, the act of observation changes the state of the system. This blurring of the lines between observer and observed led to a rethinking of objectivity. Heisenberg's principle suggested that there was no such thing as pure objectivity in the quantum world because measurement itself played an active role in shaping the reality being observed. This insight questioned whether reality could ever be fully independent of human observation. Furthermore, Heisenberg's uncertainty principle prompted a re-evaluation of the concept of determinism. Classical physics operated on the assumption that if enough information was available, the future could be predicted with precision. Heisenberg's discovery suggested that this assumption did not hold at the quantum level. Instead of a deterministic universe, quantum mechanics presents a probabilistic universe where outcomes are not strictly determined by initial conditions but are governed by probabilities. This shift from determinism to probability had a profound effect not just on science but on the broader cultural and philosophical understanding of free will, causality, and the nature of existence itself. It suggested that, at least in certain realms, the universe was not a mechanical machine, but a realm of uncertainty and chance, where the future could not be precisely predicted. The implications of Heisenberg's work were not confined to the academic realm. They had practical consequences as well. The understanding of uncertainty in quantum systems led to the development of technologies that have transformed the modern world. Quantum mechanics, guided by the insights of Heisenberg and others, gave rise to the development of technologies such as lasers, MRI machines, and quantum computers. These technologies, which rely on the principles of quantum mechanics, are central to modern communication, medicine, and computing. Despite the inherent uncertainty of quantum systems, scientists have found ways to harness this uncertainty to create groundbreaking innovations that were once considered impossible. In summary, Heisenberg's uncertainty principle had a profound impact on the scientific community, challenging the deterministic view of the universe upheld by classical physics. It introduced the concept of probabilistic behavior at the quantum level, which led to a major shift in how we understand the universe and our place within it. The principle also raised important philosophical questions about the nature of reality, knowledge, and objectivity, suggesting that the act of observation itself plays a crucial role in shaping the reality we experience. Finally, while the principle might have introduced uncertainty into the scientific framework, it also paved the way for technological advancements that have reshaped modern society. Heisenberg's uncertainty principle, which became one of the cornerstones of quantum mechanics, challenged the established scientific thinking and transformed the understanding of the universe. Before this revolutionary principle, physics operated under the assumption that the universe was deterministic, following predictable laws. The uncertainty principle demonstrated that this deterministic view was limited and could not fully describe the behavior of particles at the quantum level. This shift had profound implications for both the scientific world and philosophical thought, reshaping ideas about reality, knowledge, and even free will. At the heart of the uncertainty principle is the idea that it is impossible to simultaneously measure both the position and momentum of a particle with perfect accuracy. The more precisely one of these properties is measured, the less precisely the other can be determined. This was not due to any imperfections in measurement tools or a lack of precision. Instead, it was an inherent feature of quantum systems. It revealed that particles do not have fixed, well-defined properties until they are measured, introducing the concept of a probabilistic universe. Instead of following deterministic paths, particles exist in states of probability, and only when observed do they collapse into a definite state. This change from a deterministic to a probabilistic worldview marked a fundamental departure from classical physics, where certainty was assumed to be achievable. Heisenberg's work upended classical physics' long-standing belief in absolute certainty. In classical physics, the universe was understood as a clockwork machine, where everything from the movement of planets to the behavior of objects on Earth followed strict, predictable laws. If we knew enough about a system such as the position, velocity, and forces acting on an object, we could calculate its future state with perfect accuracy. Heisenberg's uncertainty principle, however, introduced the idea that at the quantum level, the future could not be predicted with certainty. It suggested that there are fundamental limits to how much we can know, and that uncertainty is built into the fabric of reality itself. This idea of uncertainty was not just a technical challenge to classical physics, it forced a rethinking of the very nature of knowledge. If we cannot measure the position and momentum of a particle with perfect precision, how do we know anything about the world? The uncertainty principle, in essence, questioned the assumption that scientific knowledge could ever be absolute. In classical physics, knowledge was viewed as the ability to uncover objective truths about the world through precise measurement. Heisenberg's principle, however, highlighted the limitations of this view, suggesting that even in the most controlled conditions, uncertainty is an intrinsic part of the natural world. This shift in perspective had profound consequences for the philosophy of science, as it challenged the long-held belief that human knowledge could, in principle, reach a complete understanding of the universe. The philosophical implications of Heisenberg's discovery extended to the nature of reality itself. Classical physics operated on the assumption that the universe existed independently of our observation and that the goal of science was to uncover the objective reality that existed out there, waiting to be discovered. However, Heisenberg's work revealed that the act of observation played an active role in determining the state of a quantum system. The position and momentum of particles were not fixed properties waiting to be uncovered, but instead depended on the way they were observed. This idea that the observer is fundamentally linked to the observed system raised important questions about the nature of reality. Was the universe truly independent of our perception? Or was reality something that was co-created by the observer? This shift from a deterministic view to a probabilistic one also had profound implications for the concept of free will. If the universe is governed by probabilities and uncertainty at the quantum level, it raised questions about the degree to which human behavior, too, might be influenced by probabilistic rather than deterministic forces. In classical physics, human actions could be seen as the result of deterministic forces, following a strict cause and effect chain. However, the uncertainty principle suggested that, at least at the quantum level, events could not always be precisely determined. This led to new discussions about the nature of free will, where the behavior of individuals could be influenced by random or probabilistic forces rather than being fully predetermined by prior events. Despite the philosophical and theoretical challenges it posed, the uncertainty principle led to practical technological advancements. While quantum mechanics and Heisenberg's uncertainty principle in particular might seem like abstract, theoretical concepts, they have had far-reaching consequences in technology. The development of quantum mechanics led to the invention of technologies such as lasers, MRI machines, and semiconductors. Quantum mechanics also formed the basis for the emerging field of quantum computing. While the uncertainty principle suggests that some aspects of quantum systems are inherently unknowable, it also provided the groundwork for harnessing quantum behavior in practical application. Quantum computers, for example, rely on the principles of superposition and entanglement to perform calculations in ways that classical computers cannot. These technologies are already transforming fields such as medicine, cryptography, and computing, offering the potential for solving problems that were previously thought to be intractable. In conclusion, Heisenberg's uncertainty principle changed the way we view the universe, knowledge, and even human behavior. It replaced the deterministic, mechanistic worldview with a probabilistic one, suggesting that uncertainty and unpredictability are inherent features of reality. This challenge to classical physics had far-reaching consequences, not just in the scientific community, but also in philosophy and our understanding of human existence. While it posed new questions about the nature of objective reality and free will, it also led to the development of transformative technologies that continue to shape the modern world. The uncertainty principle remains a powerful reminder of the limitations of human knowledge and the complexity of the universe we seek to understand. Heisenberg's uncertainty principle, which asserts that it is impossible to know both the exact position and momentum of a particle simultaneously with perfect precision marked a turning point in the history of science. It disrupted the deterministic worldview that had governed classical physics for centuries, replacing it with a probabilistic model of the universe. This shift fundamentally altered how scientists and philosophers understood the nature of reality, measurement, and knowledge. One of the most profound aspects of this shift is the impact on the scientific method itself. In classical physics, scientists operated under the assumption that the universe was deterministic. Everything could be predicted given enough information. If we knew the position and velocity of an object, we could predict its future trajectory with absolute certainty. This mechanistic worldview, which evolved from Newtonian mechanics, assumed that the universe functioned like a giant machine, where every interaction was determined by fixed laws. The belief was that, with sufficient knowledge and precision, humans could uncover all the mysteries of the universe and predict every future event with certainty. However, Heisenberg's uncertainty principle introduced a radical departure from this idea. At the quantum level, particles do not follow predictable, deterministic paths. Instead, their behavior is governed by probabilities. This insight revealed that there are fundamental limits to how much we can know about a system. The more precisely we measure one property, such as the position of a particle, the less precisely we can know its momentum, and vice versa. The principle highlighted the intrinsic uncertainty in nature, showing that the universe at its most fundamental level is not governed by fixed laws of motion, but by probabilities and indeterminacies. This not only shattered the certainty of classical physics, but also revealed a new way of understanding reality itself. One key consequence of the uncertainty principle was its impact on the philosophical underpinnings of science. In classical physics, knowledge was viewed as the discovery of objective truths about the universe. The scientific method operated on the premise that through careful observation, measurement, and experimentation, humans could uncover the fixed laws that governed all of nature. Heisenberg's work, however, introduced a new epistemological perspective. He showed that the act of measurement itself altered the state of the system being observed. This made it impossible to observe a system without influencing it, calling into question the idea of objective knowledge. The very process of observing a quantum system affects its state, which means that the observer is not a passive, detached entity, but an active participant in shaping the outcome. This new view of science and knowledge led to significant shifts in the philosophy of science. If the uncertainty principle implies that absolute certainty is unattainable, then what does it mean to know something? Heisenberg's work suggested that human knowledge is inherently limited, that there are aspects of reality that will always remain beyond our grasp. This acknowledgement of the limits of knowledge was a stark contrast to the optimism that had characterized the scientific revolution. Instead of assuming that science could uncover all truths, the uncertainty principle suggested that science must work with the understanding that uncertainty is built into the very fabric of reality. This philosophical shift had a lasting impact, influencing not only physicists but also philosophers who began to reconsider the role of observation, measurement, and interpretation in the construction of knowledge. Moreover, Heisenberg's principle influenced the way we think about the nature of reality itself. In classical physics, reality was thought to exist independently of the observer, and it was assumed that the task of science was to discover the objective facts about this external reality. The uncertainty principle, however, suggested that reality at the quantum level is not fixed until it is measured. A particle's position and momentum exist only in a state of probability until an observation is made, at which point it collapses into a specific state. This concept introduced a radical new idea that reality is not something that is simply observed but something that is actively created through the process of measurement. The universe, at its core, is probabilistic, and what we experience as reality is the result of the interplay between the observer and the observed. The uncertainty principle also raised questions about the nature of causality. Classical physics operated on the assumption that all events in the universe were caused by prior events, leading to a chain of causes and effects. If we could understand the initial conditions of a system, we could predict its future with certainty. However, Heisenberg's principle challenged this assumption by suggesting that, at the quantum level, events are not strictly determined by previous states. Instead, outcomes are governed by probabilities. This introduced a form of causality that was different from the strict, linear causality of classical physics. In the quantum world, causality operates in a probabilistic manner, where the future is not determined by past events but is shaped by a range of possible outcomes. This shift had deep philosophical implications, challenging the idea that the universe operates according to a rigid cause and effect structure. In addition to its philosophical and theoretical implications, Heisenberg's uncertainty principle has had practical consequences in the development of modern technology. The principles of quantum mechanics, including the uncertainty principle, have led to the development of technologies that have revolutionized the way we live and interact with the world. For instance, the development of lasers, semiconductors, and MRI machines all rely on the principles of quantum mechanics. These technologies have had a profound impact on fields such as medicine, communication, and computing, bringing about advances that were once thought impossible. Quantum computers, which leverage the strange properties of quantum particles, hold the potential to revolutionize computing by solving problems that are beyond the capabilities of classical computers. These advancements are a testament to how a fundamental understanding of the probabilistic nature of the quantum world has translated into practical innovations that shape modern life. In conclusion, Heisenberg's uncertainty principle was not just a revolutionary concept. In quantum mechanics, it was a catalyst for a broader shift in scientific thought. It challenged the deterministic worldview that had dominated classical physics, replacing it with a probabilistic model that acknowledges the inherent uncertainty in nature. This shift had profound implications for how we understand knowledge, reality, and causality, forcing us to rethink the role of the observer and the limits of human understanding. The uncertainty principle continues to shape both scientific inquiry and philosophical thought, reminding us that uncertainty is an integral part of the universe and that the pursuit of knowledge is always bounded by the limits of observation and measurement. Heisenberg's uncertainty principle is one of the most profound concepts in modern science, challenging centuries of classical thinking and redefining how we understand the universe. The principle, which asserts that it is impossible to know both the exact position and momentum of a particle at the same time, transformed the field of quantum mechanics and has continued to shape scientific thought and philosophy. In the case of the seventh keynote, the principle's impact on the relationship between science and human perception is vital, as it forces us to reconsider the nature of objectivity, reality, and how human beings perceive the world. Before Heisenberg's breakthrough, science had been firmly rooted in the classical physics model, which held that reality existed independently of human observation and could be understood through objective measurements. This model, which had flourished since the time of Newton, assumed that the universe operated like a machine, governed by strict laws that could be discovered through careful observation and calculation. In this view, the role of scientists was to uncover the objective truths about the world through measurement, and these truths were thought to be independent of the observer. However, Heisenberg's uncertainty principle shattered this assumption. In the quantum world, the act of measurement itself has a fundamental impact on the system being observed. The position and momentum of a particle are not fixed properties waiting to be uncovered, but instead are intertwined with the act of observation. The more precisely one property is measured, the less precisely the other can be known. This introduced the idea that scientific knowledge was not as objective and detached as previously thought. The observer, whether human or instrument, was an active participant in shaping the outcome of the measurement. This realization had significant implications for the philosophy of science. Classical physics had been based on the belief that the scientist could observe the world without affecting it. The concept of an objective, independent reality was central to this view. Heisenberg's principle, however, suggested that the very act of observing a quantum system altered its state, making the observer and the system inseparable. This challenged the idea of absolute objectivity in science, suggesting that knowledge could never be fully separated from the context of the observer. The uncertainty introduced by quantum mechanics, therefore, not only changed how scientists approached measurement and observation, but also led to a deeper philosophical inquiry into the limits of human understanding. Moreover, Heisenberg's uncertainty principle raised important questions about the nature of reality itself. Classical physics had assumed that the universe existed as a fixed, objective reality that could be fully understood through observation. However, quantum mechanics suggested that the very nature of reality at the microscopic level was fundamentally uncertain and indeterminate. The behavior of particles was not fixed until measured, and even then, only probabilities, not certainties, could be known. In this way, the universe was not a machine running according to predictable laws, but a realm of possibilities where events could only be described in terms of likelihoods rather than absolutes. This challenge to classical ideas of reality had far-reaching implications for how humans perceived the world around them. The belief that we could understand everything about the universe with enough observation and knowledge was a comforting idea. It gave humans the sense that they were masters of their environment, capable of discovering the laws that governed everything. Heisenberg's uncertainty principle undermined this confidence by showing that there were limits to human knowledge. No matter how advanced our technology or measurements became, there would always be aspects of reality that remained beyond our grasp. This realization forced humans to acknowledge the fundamental uncertainty and mystery that lies at the core of existence. Heisenberg's principle also led to a re-evaluation of the role of perception in shaping our understanding of the world. Classical physics had assumed that human perception was capable of accurately reflecting the external world. If we could measure something with sufficient precision, we would know it with certainty. However, quantum mechanics suggested that our perception of the world is influenced by the very act of observation. This introduced a new way of thinking about the nature of reality. It was not something that existed independently of us, but something that was actively shaped by the act of observation itself. This view of reality, where the observer and the observed are inextricably linked, has profound implications for how we understand our place in the universe and the limits of human knowledge. The uncertainty inherent in quantum mechanics has also affected our understanding of causality and free will. Classical physics held that everything in the universe operated according to deterministic laws. If we knew the position and velocity of every particle in the universe, we could predict everything that would happen in the future. However, the uncertainty principle revealed that, at the quantum level, the future is not strictly determined by the past. Instead of a predictable chain of causes and effects, quantum mechanics suggests that events occur according to probabilities. This challenges the classical idea of causality and opens up new philosophical questions about the nature of free will. If events are governed by chance rather than strict causality, can human beings be said to act with free will, or are we also subject to the same probabilistic forces that govern the quantum world? In addition to its philosophical impact, Heisenberg's uncertainty principle has had practical consequences for science and technology. The development of quantum mechanics, driven by Heisenberg's work, has led to remarkable technological advancements that have revolutionized various fields. Technologies such as lasers, MRI machines, and semiconductors are all based on principles derived from quantum mechanics. Perhaps most notably, the development of quantum computing has the potential to radically transform fields like cryptography, artificial intelligence, and complex modeling. These technologies rely on the understanding that particles can exist in multiple states at once and that they behave according to probabilistic laws. While the uncertainty of quantum mechanics presented challenges to our understanding of the universe, it has also led to innovations that were once thought to be impossible. In conclusion, Heisenberg's uncertainty principle is not just a cornerstone of quantum mechanics. It has reshaped the very way humans understand the universe. By showing that measurement and observation influence the system being studied, Heisenberg introduced a new way of thinking about knowledge, reality, and human perception. The principle forced science to confront the limits of human understanding and highlighted the uncertainty that lies at the heart of the universe. It also challenged classical ideas of objectivity, causality, and free will, raising fundamental philosophical questions about the nature of existence. While quantum mechanics has introduced a new and uncertain view of the world, it has also led to remarkable technological advancements that continue to shape modern life. Heisenberg's uncertainty principle stands as a reminder that uncertainty is not a flaw to be overcome, but an intrinsic feature of the universe itself.